Today we'll learn about linked lists. So what is a linked list? What do we understand by linked list? So if we look at the word linked list, it means there is a list and it has links. So there is a list of items that are linked, right? So if I have a list of items and then I put links in between them, so this is something what I can term as a linked list, right? Now this linked list can be of anything. These things can be anything. These things can be any user data type. So this could be a structure, this could be an integer, this could be a float, anything, right? So what are the necessary conditions for a data structure? When do we call a data structure a linked list? So the data structure has to be linear. Linear means these connections are one to one. They are not one too many. No. Secondly, this has to be a null terminated data structure. That means you start and then you end. And in between, everything is linearly connected, linear connections, right? Then it has to be dynamic in nature. Dynamic means it's on demand, allocation, and deallocation of memory, right? So essentially, we can grow or reduce in size as our programming software requires. It is bound by availability of memory and else it can grow, right? So until and unless we have the end of or the exhaustion of our whole available free memory, the data structure can continue to grow. Now, what would be the operations, typical operations? Typical operations here would be add or insert, which basically adds a new data. We could have delete or remove a particular node. We could find or what search for a particular data. We could delete all, like completely purge the whole data structure. We could replace, find and replace data. And we could say give a size or count of the number of nodes that are there in the linked list, right? So another thing to understand is what is the motivation? What is the motivation behind having a linked list? So far, most of you would already know about arrays. So array is something like int array 10, right? Or 20 or 30 or any value k or n for that matter, right? So array is capable of having a user defined or a compiler defined data type. So why do we require linked list? Why? Obviously, we always require a linked list because it suits some particular use case. Even though we have array, array does not fit all use cases, does not fit all solutions, right? Consider we have a program and I have an input buffer in this. So I have this buffer so that stores user data that is produced. You can say produced, and then it pushes this onto program 2 that basically processes this data. Now, if the process for program 2 this gets stalled or this goes into wait state for whatever reasons, so program 1 has to continue to take user data. What if we choose array to be the data structure for buffer? That means we have fixed scope. So if this thread gets stalled for say 10 cycles and I have a buffer of 10 units here, then I am running into overflow the moment user enters the 11th unit here. During these 10 cycles. So to do away with this thing, we do allocate dynamically allocated data structures. This is just one example. So where we are not bound by limitation of rigidity in design. So array is rigid. That means if the buffer was full, that means we had to allocate new buffer. That could fill in more data. Now, try to understand. So we have two choices here. So we allocate a new buffer, which is say a secondary buffer, right? Or we enlarge the existing buffer. So the way to do it is get larger buffer and then copy over the data. If we choose this, then this is additional bookkeeping because the moment the stall state is gone and we start processing, this whole memory allocation must be deallocated. But before we do that, so processing happens on first in, first out basis. So your most latest data is still in the old buffer, and then you are maintaining this new buffer with new data. So this is unnecessary bookkeeping, right? Because then arrays are very difficult. So you'll keep popping data from here, and till the time you have to keep adding more stuff here because you can't circle around to this, right? Or then otherwise you have to have a circular buffer, but then it will overrun. Circular buffers have a limited capacity. Now, in case we do this, to maintain the sanctity on bookkeeping, if we do this, that means we are losing performance because a lot of time will only get consumed in copying this data over from buffer 0 to buffer 1, right? So it becomes important that we have a linked list like structure which is self-sufficient with respect to bookkeeping, as well as dynamic with respect to size. Another advantage is that allocating and deallocating big chunks versus singular data points, data elements. So in linked list, we allocate and deallocate for singular data elements, and arrays, we have to do this in big chunks. So this causes segmentation as well as inefficient use of memory. But this decreases segmentation and is more efficient operationally because we are allocating and deallocating smaller chunks. Secondly, a linked list is self-sufficient. You do not need additional space to store anything. So each node will basically take its own space for the bookkeeping of the next pointer, and that's all that you need. So we just need one head pointer and each node has to store the next pointer. So that's all that we need for linked list. So let's look at what a typical linked list looks like. Let's first look at the node. Node is one data representation plus all the bookkeeping resources. So for linked list, the node would look like data type and then the data variable and then the next linked list node pointer, right? So this is what it will have. So this data type is custom. So you can have user as well as preset data type that comes with particular languages and compilers. And then this is a pointer to the node. So you have to understand. So this is a pointer. So this is a pointer to a node of the same type. So make sure that you understand that this is a pointer and not a node. So in essence, if you look at the memory, your node has two parts, data and address. So the data is whatever structure or integer or float or character or any other data type or class that you have. So class object basically. So and the address is basically the pointer variable to next node. So somewhere in the memory, it could be contiguous also, it could be non-contiguous also. There will be an address for, say, this is data 0 and this is data 1. So this will carry the address of data 1. And then this address here will carry address of data 2. Something like this. So in memory, we need to have an additional head pointer variable. So this variable will basically point to address of data 0. And then once we have the address of data 0 and we have reached here, then we know how to traverse, because then we know the address to this, and through this we know the address to this, and there will come a point where this is null. So in X, Y, Z, A, B, C, D, E, F, G, H, M, N, O, P, Q, R, S, T, V. So in all this random memory, what we are reading as ASCII characters here lies our actual data structure, which is a linked list. So today we have understood what a linked list is, how it is different from array, and the kind of advantages that it presents. In the next lecture, we'll go ahead and learn more about linked lists.